So it's a pleasure to have Alan Reid come back. He mentioned in the lunch for the graduate students that this was his first job. He was first here from 1987 to 1990 as a postdoc. I think it's always good to have our postdocs come back so they can recall what big-time mathematics is like. Alan has been in some other institutions. Like he was for 21 years, he was at UT Austin, where he was a chair professor in the chair for years, and he had 16 graduate students who just came back from one of his mathematical grandsons giving a talk, and he told me he couldn't remember how many mathematical grandsons he had, but it's more than one. Since this fall, he's been the Edward Odell Levitt Professor at Rice University. He's speaking at the ICM in the Geometry and Topology seminar. The ICM in Geometry and Topology in Rio, and and today he's going to tell us about profinite rigidity.
Well, thanks very much, Mike. Maybe I should just stop here, actually. I mean, it can only go downhill from what Mike just talked about. But anyway, it's a great pleasure to be back here. And as I said, as Mike said, that I came here 30 years ago this past September, and had really happy times here, and it was very formative in my mathematical development, being here with people like Mike, and like Dan was here, and Walter Neumann in particular was here. It was a really good time for me to be at Ohio State, and there's lots of familiar faces in the audience, and there's lots of unfamiliar faces in the audience, which is probably good for Ohio State. But anyway, it's a great pleasure to be back here. So what I'd like to talk about is this title of profinite rigidity. And I'm not really going to get into any technical proofs of anything. What I'd like to sort of really talk about is just the context for this work. Some survey some broad ideas of where we're trying to go, give some ideas of what tools can be brought to bear, in particular the recent developments of Hegel and Wise and three-manifold topology and geometric group theory have been kind of important tools for us as well. And I say us, so all of this is kind of an ongoing program with Martin Breitson. We're joint with Martin Breitson, who I should also say, the first time I met Martin was here. We had a special semester that Walter organized back in 1990. Martin was a graduate student of Kevin Volkman at Cornell, and he came and gave some talks on his work on cat zero, and I forget exactly what it was, but it was cat zero, not cube complexes back then, but cat zero spaces. Anyways, the first time I met Martin was here, so there's a lot of happy memories for being back in Columbus. Okay, so let me make some standing assumptions. Okay, all groups are finitely generated. And occasionally there'll be the need for these groups to be finitely presented, and probably I'll just forget to say it, but if there's a need to say the word finite presentation, just assume that it has to be said, and just don't bother thinking about interrupting. So all groups are finitely generated, sometimes they're finitely presented. Now, I also want to consider infinite groups, but I also want these infinite groups to have a large supply of finite quotients. And one nice way to phrase that is that all groups are residually finite. And so by this I mean, again, just for recollection's sake, if we've got a gamma some group, and we've got gamma, little gamma there, which is a non-trivial element, well, to be residually finite means we can find a finite quotient of gamma so that the image of gamma, little gamma, is non-trivial. So there exists phi from gamma to A, where A is finite, and phi gamma is not 1. So for all gamma there, we can find that quotient. So that's what residually finite means. So that gives you some rich supply of finite quotients with which to work with. And at least in my office, previously at UT Austin, but now at Rice, the classes of residually finite groups that I like, well, the ones that everybody likes. So if we've got gamma in GLNC is finitely generated, then this guy is residually finite. Again, FG, and this is just Maltse's theorem. And then, you know, germane to some of the things that I'll talk about today, if we look at the fundamental group of a compact three-manifold, then the fundamental group of this guy is residually finite, and this follows, you know, by the geometrization conjecture solution by Perlman using arguments of Hempel and Thurston. So that's kind of a rich supply of finite quotients. Okay, so the motivating question, no, let's just see here. Let's go here first. No, don't do there. Okay, thanks, Mike. So the motivating. Question is to what extent the finite quotients of the group gamma determine the group gamma. And we'll zoom in on more precise statements. So to what extent you finite quotients of gamma determine gamma. Okay. So let's make that a little bit more precise. So let's let, make a definition here. So let's let C of gamma be the collection of A such that A is a finite quotient of gamma. So maybe I should put square brackets here just to indicate isomorphism classes of finite quotients. And again, I don't really care if A shows up as a finite quotient in a million different ways. So long as A occurs as a finite quotient, it just goes on the list. Okay, so it's just a set of isomorphism classes of finite quotients. There's no other structure there. Okay, it's just a set. Okay, so then the question is, if C gamma is equal to C delta is gamma isomorphic to delta, or maybe one could also ask what question prime, you know, when does C gamma isomorphic to C delta imply that gamma is isomorphic to delta? So that's kind of the structural question that I'd like to talk about. And just for the sake of introducing some other kind of notation, which it won't be quite so bad in this talk, but usually there's a significant amount of bad notation that appears in some version of this talk. None of that's due to me, but it's just due to other people that I have then got to use. So the first part is the following, but let's let G of gamma be equal to those delta with the same finite quotient as gamma. Now this G here, this stands for the genus of gamma. Now, of course, being a low-dimensional topologist, perhaps, me, you know, genus means something. And it ain't that, obviously, here. So what's genus meant to be reflective of in this case? Well, if you think about the theory of integral quadratic forms, there's a notion of genus there. So genus there means that you've got these binary quadratic forms over Z that are equivalent locally at all places, but they're not necessarily equivalent over the whole of Q. So that's really the reason for the word genus. So let me just maybe say a little bit of what the local to global picture is meant to be in this setting. So it's a Y genus. Okay, so the local picture. So what could the local data be in this case? Well, we've got this finitely generated group gamma. So you fix a finite generating set for gamma, let's call that S. And then we've got this collection of finite quotients. So we push that generating set forward and we get finite collection of generators for some finite groups, we can build the Cayley graph for both the infinite group and for these finite groups. So for each of these finite groups, we've got these Cayley graphs that we've built. Now, because the group is residually finite, you know, huge balls in the Cayley graph here embed in Cayley graphs downstairs. So what we see for local data, really, is these Cayley graphs of these finite quotients. So the local data is the Cayley graphs of the finite quotients. And the global data is how you piece these together. Can you piece these together only to get gamma, or is there ways of piecing them together and that in fact give different kinds of groups? So the global picture is to recover gamma using these Cayley graphs. So that's really the reason, perhaps, that the word genus is included here. And just sometimes it'll be helpful that instead of just looking at the class of all finitely generated residually finite groups, it's sometimes helpful just to specialize. So it's sometimes helpful to consider the genus in some restricted class. So let's just maybe say that if P is some class of groups, then, you know, GP of gamma is just those delta in the class of gamma with C of gamma equal to C of delta. So let me just make a comment going back to this, you know, use of the word residually finite. So if I didn't put in something like that, it's easy to come up with cheap examples of infinite groups with the same finite quotients. I just take my favorite group gamma, and then I just free product, say, with some infinite simple group. And then, okay, they've got the same finite quotient, so I can just stop there. But of course, that group isn't residually finite, and so by insisting that we live in the world of finitely generated residually finite groups, one can get rid of sort of silliness that one obviously has to deal with. Okay. Okay, so again, the question now is, again, there's really two questions that, you know, for which gamma does G gamma equal gamma? And, you know, when is, this is 2, is 1, and when is G gamma got cardinality bigger than 1, and what can you say about groups in the same genus? What kind of properties?
G gamma equal to gamma.
Simply meaning
Gamma is a set. G gamma is a set.
Right. So that's curly brackets to indicate that's the singleton set containing gamma. Okay. So the genus is the collection of those guys with the same finite quotients. So when I write that, it means it's only gamma. Right. Okay. So let me
Boards can move.
Huh?
You can move the boards.
You just told me not to move.
I didn't tell you.
Okay, so I can do that.
There's another movable one.
Yeah, so I can work on this one. Okay, so let's do an example. So let's prove that the genus of the infinite cyclic group is just the infinite cyclic group. So Z is determined by finite quotients, and there's no prizes for this one, but we'll talk it through just because we can. It'll be the only real proof of any, well, it's not very significant, but it's the only proof you're going to see. So let's just prove this. So again, we're working within the class of residually finite groups. So suppose we've got, you know, lambda, say, in the genus of Z. Well, let's assume that lambda is not abelian. So what does that mean? Well, it means that there exists some commutator that's not trivial. Okay, now by residual finiteness, there's a finite quotient that doesn't kill that. Okay, by RF, there exists I from lambda to A, where A finite, and phi of C is not trivial. but we've got the same finite quotients as Z. So therefore that must kill the commutator. So that can't happen. So therefore it cannot be well, it must be abelian. I'm not going to write cannot be not abelian. It must be abelian. But now if you think about this, that the structure theory for finitely generated abelian groups then tells you, well, the only thing you can possibly see is Z. Because if I gave you kind of Z cross Z plus Z mod 3Z, well, I can visibly construct some finite quotients that are not finite quotients of Z. So then the structure theory for finitely generated abelian groups implies that lambda must be isomorphic to Z. Okay, so this is a very elementary argument, and in fact, this can be, improved to give that if we take G to be gamma, where this is a finitely generated abelian group, then this argument shows again that you get this. You can only have gamma in the genus, again, simply because it has to be abelian, and then the structure theory for abelian groups allows you to construct finite quotients that wouldn't be there if it was different. So one upshot of this is, so a corollary of this is that if we're now in general, if gamma and delta have the same finite quotients, then it turns out that the abelianization, or H1 gamma Z, these must be isomorphic. Okay, so the finite abelian quotients are the same. In fact, that can be bootstrapped into the same statement that the first homology groups must be isomorphic for the same kinds of arguments. Otherwise, you can construct some finite abelian group that would be a quotient of one, but not the other. Okay, now, this is all kind of fairly elementary, and I can see there's sort of muffled laughter somewhere in the back row. But in fact, you don't have to really work much harder to produce examples of groups that are virtually Z, have the same finite quotients, but are not isomorphic. So there's a great little paper by Baumslag who gives a construction. So Baumslag, and let me write down kind of a more general statement that gives a way to construct classes of groups with the same finite quotients. And this is almost something that you can do in an undergraduate group theory class. I mean, there's one point here that you need something like the Riemann-Kroll-Schmidt theorem that probably one doesn't see in an undergraduate class, and probably shouldn't. But anyway, so he says we've got A and B. It's kind of a stabilization with A cross Z isomorphic to B cross Z. So you stabilize by tagging on Z's. Then, in fact, that A and B have got the same finite quotients. So this gives a mechanism whereby you can construct groups with the same finite quotients, particularly when it's coupled with looking at extensions of group by outer automorphisms of things of finite order, which I'm not going to touch on, but this is how Baumslag constructs his example. So he uses this to give the following construction. We've got 1 to C to gamma 1 to Z to 1. And there's gamma 2 to Z to 1 to C to 1, where C is some finite group. And really the condition that one needs for this is that, basically C shouldn't have order 1, 2, 3, 4, or 6. You have to have an outer automorphism of a particular order, but you don't have to work very hard. You can take the cyclic group of order 11 in this. And what Baumslag shows is that you can do this construction kind of using this in such a way that gamma 1 is not isomorphic to gamma 2, but in fact these two groups can be proven to have the same finite quotient using this construction here. You can just kind of wash out the extension by stabilizing with Z. So this is kind of a nice kind of basic construction of giving examples of groups with the same finite quotients. Now, as it turns out, proving this kind of rigidity statement that there is only the group in its genus, that turns out to be much harder, and we'll get to that shortly. Okay, so let me just mention a few other kind of examples and results before I go on to some more recent stuff. Mike just said there was other blackboards somewhere. Okay. Okay, so let's just maybe, so what, some other. Okay, so let me just mention a few. There's a lot known about this question when you can construct various classes with the same finite quotient. So in the world of nilpotent groups, it's well understood. And I just like saying this part because it's by a guy called Pickle, that was a graduate student of Bounslag at Rice, which is kind of cute. And he did some very nice work on this question of the genera of nilpotent groups. So by saying well understood, basically what he proves is that there are only finitely many nilpotent groups in the genus. And there's kind of a way to enumerate these. And there are examples of nilpotent groups that are the unique guy in their genus. So there are examples of such things. So the nilpotent case is well understood. Perhaps more reasonably in my office, the kinds of things that I like are lattices and semi-simple Lie groups. So in this case, there exist lattices in semi-simple Lie groups, let's say gamma 1, gamma 2, with these guys having the same finite quotient. Again, it's known in these cases that the genus is finite. So for the constructions that are given, it's known that the genus is finite. Now, where do these come from? Well, like many of these kind of constructions, number theory is kind of lurking in the background. So here, the number theory is an application of the so-called congruent subgroup property that allows you to get complete control of finite quotients. I'm not going to get into that too much details, but just if one thinks of SLNZ, there's a collection of finite quotients one gets by taking SLNZ mod MZ, and you have the congruent subgroup property if basically that's all the finite quotients you have. Now SL2Z doesn't have that property, but everything else above 2 does have that property. And in high rank, there's lots of constructions of lattices that have the congruent subgroup property that one can use to give examples of groups with the same finite quotients. And what's the number theoretic input? Well, there are examples of number fields that have got the same zeta function, but are non-isomorphic, and that gives you the splitting type of prime ideals, and that's all you need to build these kinds of constructions. Okay, so that's one class of examples that lives in my office. And the other kind of examples that live in my office are the fundamental groups of 3 manifolds. And so there are examples, so there exists closed geometric 3 manifolds. M such that this is bigger than 1, i.e. that there are also, turns out, closed 3 manifolds with the same geometric structure as M that have the same finite quotients as M, but are not homeomorphic. And again, what's going on in these kinds of constructions, either it's kind of number theory that gives you certain solvable quotients, or one can construct Seifert-Fibert spaces where one can apply this kind of picture here to kind of wash out extensions that you get that build up this group. But again, I don't really want to get into the details of that, but I'm happy to talk later. And let me just mention that there's examples of Brightson that built on his work with Grunewald that give finitely presented groups with the gamma, with the genus being infinite. So there are examples. So for finitely generated groups, this was known before, but for finitely presented groups, there's a construction of Brightson that does that. Okay, so the focus today is groups that occur naturally in low-dimensional topology. And low means dimensions 2 and 3. So focus. Okay. So groups. from low-dimensional topology. So that we mean sort of free groups, fundamental groups of closed orientable surfaces. So this is Fm, where m is at least 2, and here G is bigger than or equal to 2. Fundamental groups of compact 3 manifolds. And, you know, within this finite volume hyperbolic 3 manifolds. Pi 1. And really, the motivating interest for Martin and I is really the case of the free group. So it's an old question that goes back to the 70s. And I'll be able to say this, but I won't be able to spell it. Remeslenikov. And the question is that, you know, is the free group determined by its finite quotient? Okay, and we're equal to 2. So we've seen that for Z, and the question is that true for n bigger than or equal to 2? Now, if you think about that for a minute, you think, well, come on, you know, we must be able to do that. So the question's kind of the following. Here's the free group of rank 2. Okay, we know all the finite quotients of the free group of rank 2. It's all finite groups can be generated by most 2 elements. Well, that's good news. So the question is, could you have this, you know, million generator group living over there so that all its finite quotients are just 2 generated at worst? So that's the question, and you think, well, come on, you must be able to do that, and maybe you can, and if you can, please do tell me, because I'll be very interested. But this is still an open question, and one can maybe begin to speculate, because of, you know, work of myself and Brightson, that maybe the answer to this is yes, and ditto for surface group. So is G of pi 1 sigma G equals pi 1 sigma G. Now, I've already told you that there are compact 3 manifolds for which it isn't going to be true. There are constructions of such things. And again, the point is that if we stick now to the finite volume hyperbolic world, again, the evidence might be moving towards hyperbolic 3 manifold is just the same thing. Okay, so they should be kind of rigid in this sense, that things with the same finite quotients should just be it. Now, just as an exercise for the reader. So if I've got to convince you that, for example, free groups are determined by their finite quotients, well, maybe we can just warm up by convincing ourselves that you can distinguish the free group from a surface group in finite quotients. So the exercise is distinguish Fn from pi 1 of sigma G. Now, what I told you before, if this is a surface group of genus G, then the only possibility using H1 is that this should be F2G. Okay, so the task is to distinguish the free group of rank 2G from a surface group of genus G. Now, one can do this in many ways, but one can do this by brute force. One can actually write down finite groups that occur as quotients of this, but not of that. Now, how can you do that? Well, I'm not going to give the hint away, but the point here is that in the free group, okay, the rank of H1 can alternate from odd to even. For a surface group, it's always even. It's rank 2G. And that can be captured in finite quotients by building an appropriate finite quotient. So these guys, you know, you can be distinguished by finite quotients. But then you begin to say, well, you know, how do I distinguish, say, the free group from some 3 manifold group? And I'll give an example later just to indicate some of the difficulty of that. Actually, maybe I'll just do it. Maybe I'll just do that now, in fact, since I mentioned it. So here's an example of a link in the 3 sphere that the fundamental group is very hard to distinguish from the free group of rank 2. All right, so bear with me here. You shouldn't really do these things in public, but No, did I do that? I know I did that wrong, I think. Did I? Hang on. There. No, that's right. Come out of there. And right there. Come out of here. Okay, now with good luck and a fair wind, that is a link of two components. It's a link of two components. Namely, there's the unknotted component here, and then there's a connect sum of two trefoils that you'll see there. So let's call that link L. So then, you know, S3 minus L, in fact, looks like H3 mod gamma for some lattice gamma in PSL2C. So H3 is just a upper half free space model of hyperbolic space, too germane to what that is today. But we get some discrete suburb of PSL2C. Okay, so this guy is quite hard to distinguish from the free group of rank 2. So for example, this group gamma has the same lower central series quotients as F2. So in particular, that means that all finite nilpotent groups are the same. And it surjects all two-generator finite groups. So if you've got to distinguish this guy, you've got to find some non-two-generator group that distinguishes that guy from the free group of rank 2. Now, if you've ever thought about that, kind of writing down non-trivial finite groups that are three-generator but not two-generator is non-trivial. And I don't know an explicit, I mean, I could probably do it by magma or something, but one can distinguish these guys, but not using kind of finite quotients explicitly, more rather some other techniques that we bring to bear to distinguish the class of three manifold groups from surface groups. So, apropos of that, let me just state a theorem that Martin Breitson and Martin Conderoy proved a few years ago. The theorem. So if we let's let L be the collection of groups that occur as lattices in connected Lie groups. Now, free groups and surface groups, these are special cases of Fuchsian groups. So these are guys that act properly discontinuously on the hyperbolic plane. So let's let gamma equal to a finitely generated Fuchsian group. So this is discrete. In PSL2R. Then if we look at the restricted genus, i.e. only compare gamma to lattices and connected Lie groups, then in fact, gamma is determined by its finite quotients. And in some sense, the hard case, as I'll mention briefly later, is distinguishing two Fuchsian groups by their finite quotients. So this theorem, takes care of this. The free group can be realized as a lattice in SL2R, and this is a lattice in SL2C or PSL2C. So therefore, I know that that guy doesn't have the same finite quotients as this free group. Okay. And maybe one other little comment to make before I get on to talking about the word profinite that appears in the title. So let's make there's a kind of little, well, I hesitate to call it a theorem, but something that Martin and I proved some time ago. Again, from the perspective of what kind of groups can be in the genus of a free group. If there was something with the same finite quotients of a free group, what the heck can that look like? Now we do know some structural properties about that group, but here's kind of a theorem that's. That's an L. L is a collection of lattices in connected Lie groups. So remember, the decoration means I'm only comparing the group to the classes of groups.
I don't get why this is a counterexample to that.
Well, because.
Oh, given connected Lie group.
Yeah, so this guy here, right, that's a lattice in SL2C,
yeah.
Not an SL2R.
Oh, okay.
So that's, so.
You need the SL2 Lie group the same.
Right. Okay, so let me just make a comment here. So there's a lot of interest in from the world of word hyperbolic groups on two questions. So, so let me just see how do I want to phrase this? Okay, so let's do it like this. So if gamma is has the same finite quotients as a free group of rank at least 2, and gamma here is one-ended and hyperbolic. So you can just think of, you know, gamma just being freely indecomposable and sort of contains a free group or something interesting. Then, if there is such a guy, then either there exists a word hyperbolic group or hyperbolic group that's not residually finite, or there exists a one-ended hyperbolic group that does not contain a surface subgroup. So there's been a huge amount of activity on constructing surface subgroups following Kohn-Markovich. Now I should really put in a little decoration here, quasi-convex. There's some condition on the surface subgroup, but it's very natural from the point of view of geometry. So if there is a guy in the same genus here, then there has to be one of these pathologies that happen. And people have spent a lot of time, well, I think well, I don't know, for most people, depends who you talk to, but there's some belief that that case shouldn't happen. There should be word hyperbolic groups that are not residually finite. Okay. Right-ho. So let me now talk a little bit about organizing some of our ideas and touching on some of the techniques that we bring to bear more recently. And
so those are two conjectures of Gromov, and then
right. They're being played off against each other there. Okay, so how do we organize finite quotients? Okay, so the profinite completion. Okay, so if you've got our group gamma here, which we'll assume is finitely generated, you don't really need residually finiteness for this statement, but it's always good to have in mind. And then we'll let script n be the collection of normal subgroups of finite index in gamma. So the profinite completion is a way to organize this. So what is this gadget? Well, it's the inverse limit of the inverse system that you get from these finite quotients G mod n. Now, if you haven't seen the profinite completion before, you know, there's nothing I can usefully say in like 5 minutes that's going to be helpful. Let's just say that it's organized. So the good news is it's organized into some compact, totally disconnected topological group. And the bad news is it's organized into a compact, totally disconnected topological group. So you don't actually think you've made progress, but in fact, there's very strong connections between the subgroup structure of the profinite completion and the discrete group. So one other way to maybe think about this is that we can think of gamma with a map that goes to the product of these finite groups. So we can topologize these with a discrete topology. So they're compact. So then we get that this is some compact space here. And we've got a map, call it I, that sends a gamma. Well, it's just this giant, you know, infinite vector that you get one for each normal subgroup of finite index.
G is down.
G is, yeah, sorry. With a backslash. Yeah, thank you. So gamma mod n. And then what this profinite completion is that it's just the closure of the image of gamma. So one way to sort of concretely think of that profinite completion is as a subgroup of this giant direct product here. And the point is that it, you know, it's in this direct product and there are these connecting homomorphisms that go between various finite quotients. Okay, so that's the good news. You've organized the finite quotients. And one little remark is that the finite quotients of gamma are the finite quotients of gamma hat. That, you know, given a finite quotient of gamma hat, you can build a finite quotient of gamma. Given a finite quotient of gamma, you get a finite quotient of gamma hat. Now, what's sort of a classical theorem from the world of profinite groups is that in our context, if we've got two finitely generated groups with the same finite quotient, well, this is true if and only if, in fact, the profinite completions are isomorphic. So if these two things are isomorphic, then this is the same and then that's the same. So that's kind of easy to take. But it's going this way, that just the set of finite quotients, there was no decoration in that set, it was just the list of these finite quotients, is enough to recover the profinite completions. And this can be also taken to be an abstract isomorphism. If you look at the old papers, they insist on a topological isomorphism, but work of Nikolov and Siegel allow you just to take that to be an abstract isomorphism now. So then the question of which groups, when these two sets are the same becomes a question of when the profinite completions are isomorphic. So we'll say that gamma, so a definition, gamma is profinitely rigid if, gamma hat isomorphic to lambda hat implies gamma isomorphic to lambda. So the work that Martin and I have been working on recently has been trying to prove various profinite rigidity statements, both in a restricted sense and in kind of the absolute sense for certain classes of groups that I'm going to talk about now. Now, let me just make a point here that one might think, well, okay, that's all finite quotients. Maybe you can just weaken things and work with pro-p completions. So that's maybe an easier thing to work with. You can't hope to do that because, these guys here, this link group has the same pro-p completion for every prime p as the free group of rank 2. And the reason for that is it has the same lower central series as this free group. So you cannot expect to be able to distinguish things just using the pro-p world. You have to pass to the profinite world. Getting to this part here, how does part of this go? Well, we've got lattices and connected Lie groups. Well, one thing is that one can show using the Luke approximation theorem that the first L2 Betti number is a profinite invariant. So this guy here, if you're a Fuchsian group, the first L2 Betti number is just the Euler characteristic. But typically for these symmetric spaces, the first L2 Betti number is 0. So you can just throw these out right away. So once you've set up the machinery of profinite completions, it's a very easy consequence if you use a little bit of group theory to prove the first part of that you restrict basically to Fuchsian groups. And that's really how that goes.
That was the proof.
Basically the proof. There's a little bit of fiddle faddling, but that's the proof. The hard part is when you want to try and compare gamma, which is Fuchsian, with some other guy that's Fuchsian. So then you get into the question of, well, basically you've got these two spheres with marked points, and you want to make sure that the marked points line up correctly. So one thing that you might want to say is you want to rule out fake torsion in the profinite completion. So you've got this group gamma, from the structure theory of Fuchsian groups, what the elements of finite order are there. Could it be that torsion miraculously appears in the profinite completion? Now, just as a cautionary tale, the profinite world, makes your eyes go black because you can take torsion-free subgroups of SL3Z, and so they have no elements of finite order, but nevertheless, their profinite completion contains elements of all orders. So the congruent subgroup property actually can be used to build fake torsion in the profinite completion. So again, it's one of those weirdnesses that if you're a geometric group theorist or topologist, that just seems kind of freaky. There are other sort of freaky things that I'll mention later. Okay, so maybe we'll now get to the world of three manifolds. Okay, so let's let M be the class pi1 of M when M is a compact three manifold. And just as a word of warning here, finite volume hyperbolic three manifolds can be non-compact, so we could take the complement of that link there. However, I can view those manifolds as the interior of a compact three manifold with torus boundaries. So I can go willy-nilly between statements about compact three manifold and still have pictures like this in my mind when I'm thinking about such things. So let me write down a very striking theorem here that, again, gives evidence to the power of finite quotients. Okay, so this was a theorem of Henry Walton and Pavel Zaleski. So let's let M be a closed orientable geometric three-manifold. And let's let N be in script N, okay? Or I1 of N be inside there. So it's a fundamental group of some compact three-manifold. Okay, so then the statement, and assume that I1 of N has the same finite quotients as I1 of N. So we're just comparing fundamental groups of compact three-manifolds with this kind of geometric three-manifold N. So the conclusion is then N is geometric with the same geometric structure. So if you think about that, it's kind of saying you just in the sense of Thurston. Exactly. So it's geometric in the sense of one being uniformized with one of Thurston's 8 geometries. So in particular, if this M here was hyperbolic, it's kind of saying that the finite quotients recognizes it's hyperbolic, and therefore, you know, it sees that. And when you think about that, that's kind of miraculous that finite quotients can see geometry. It's a very powerful statement. And maybe a couple of things to remark upon there. So maybe just the remarks. Okay, so the first thing is, well, you know, N could be a connect sum of stuff. Well, again, you can deal with that fairly easily because the first L2-Betty number recognizes connect sums. And basically all of these guys are first L2-Betty number 0. So you can deal with that quite efficiently. So you can detect connect sum. You can also detect the fact that, well, suppose I was comparing, so N here, suppose that was some compact three-manifold with non-empty boundary. So like the fundamental group of a not complement. So you have this Z cross Z in the fundamental group. Now the profinite, so that if M here was hyperbolic, so let me just write this. So suppose that M is hyperbolic and N is compact with T2 boundary, just the incompressible torus boundary, then the fundamental group of M here does not have Z cross Z. That's one of the conditions. And the question is, well, could Z cross Z somehow show up in a fake way in the profinite completion? Well, the answer to that is no. So there are no fake Z cross Zs contained inside the fundamental, the profinite completion. So this was something that, you know, Wilton and Zaleski had to deal with. In fact, one can get around this in this particular case here. So in this case,
M can be finite volume. So M can have a,
so if M is closed, right? So if M is closed here,
okay,
then there's no Z cross Z in the actual discrete group. But you have to rule out the fact that the profinite completion may have these fake Z cross Zs, or Z hat cross Z hat, that appears. So no fake Z hat. That. But in fact, one can also deal with this using the work of Egel and Wise, and this has been useful more generally, that the profinite completion sees cohomological dimension. So in this case here, this is a closed orientable three-manifold, so there's a class in H3 that one sees. But if you've got a compact manifold with torus boundary, you know, cohomological dimension is 2. And it's a consequence of the work of Egel and Wise, and some others, but basically Egel and Wise, that there's a theory of the cohomology of, continuous cohomology of profinite groups, and you can compare that with the cohomology of the discrete group. So if you have the right modules here, you have HQ. So you got this injection, if you're residually finite, from gamma to gamma hat. If you look at the continuous cohomology of the profinite completion with some finite module coefficients, and look at that map to HQ gamma M, just the discrete group cohomology. If this is an isomorphism for all Q, Serre called this good. So there's kind of a little part of his book on Galois cohomology that's kind of great. He introduces this kind of notion of goodness and proves some interesting properties of it. But it's very hard to prove that groups are good. But as a consequence of this work of Egel and Wise, that compact three-manifold groups are good. And so you can recognize, you know, compact closed from non-closed examples. So this is a kind of very beautiful kind of theorem that sees the geometry, and part of that uses this kind of work that's consequences of Egel and Wise. Okay, so there was some other work of Brighton and myself that I was going to talk a little bit about, but I think maybe what I'll do is just finish by mentioning what I think is perhaps the best progress on this question as to whether free groups or surface groups or the fundamental groups of hyperbolic three manifolds are determined by their finite quotient. So there's no interesting examples of such groups. So the only groups that we know are determined by their finite quotients, usually there's some verbal law that's satisfied by the group, like there's no potent groups or something. So in recent work with Brightson and former student McReynolds and current grandchild Ryan Spitler, his mathematical brother, we've given an example of a clanging group. It's a theorem that hopefully will be done soon. Brightson, McReynolds, Reid, and Spitler. If you look at the group PSL2Z omega, where omega squared plus omega plus 1 is 0, so it's one of these Bianchi group that I talked about at lunchtime. If you look at the genus of this guy, so this guy's a discrete subgroup of PSL2C. It acts on H3. It has quotient with finite volume. It doesn't give you a manifold because there's elements of finite order, but nevertheless, it's basically that. So what we prove is that the genus of this group is just itself. So as I said, this seems to be the first example of what might be called an interesting group that's determined by its profinite completion. And the fact that this works is a total miracle. I mean, I don't say that lightly. I mean, there was a program to handle things like SL3Z, and you can run that program on SL3Z, and you get part way. And what you get down to a point where you're trying to understand subgroups of, say, SL3Z or this group that could have the same profinite completion as the ambient group. Now here, the good news is, this is a three orbifold group. This is the stuff I learned here, understanding three-dimensional orbifolds. Understanding subgroups of SL3Z, well, that's really, really complicated. And so one of the progresses is that this group has certain rigidity properties that higher rank lattices have, that this guy should have no business having, but it does have. And one can say very strong things about quotients of the form PSL2 of a finite field that one can use to get additional control. So the fact that this thing exists is really kind of miraculous. There's one other group that we can handle, but it's really very special amongst the family of Bianchi groups. And even tweaking this argument a little bit seems like it's just doomed to fail. So I think on that happy note, I'll stop there. Oh, it's just a cheap one, Jim. It's like the Z2 extension of that, PGL2, Z adjoint omega. Now, you may wonder, well, how come PSL2 Z adjoint I, for instance? Why does that not work? Well, the problem is that these orbifolds are non-compact. So if you look at H3 modulo one of these Bianchi groups where OD is a ring of integers, well, the cusps of this look like Euclidean orbifolds across a half-open interval. Now, for most of them, they look like tori across a half-open interval, and you can do Dane surgery and you get non-trivial character varieties. So you don't have any kind of real control in representations. That's bad. Now, Z adjoin I, it's not a torus that's the cusp end. It's a sphere with 4 mark points of cone angle pi. One can still make sense of Dane surgery there. And then finally, for this guy, the reason it's special is that the end kind of looks like, you know, one of Mike's favorite ones, where the cone angle here is all 2 pi over 3. So it's one of these Euclidean spherical, one of these Euclidean two orbifolds. And these guys are rigid. You cannot do Dane surgery on these guys. And so therefore, the character varieties of this guy is very different from the character variety of these guys here. And that's kind of a crucial thing. But it's more than just a character variety being finite. One really can say that there's really just 2 interesting representations in the PSLP.
What if you did Coxer groups, like Coxer orbifolds? Would they be rigid?
You mean in the...
For 3 manifold? Is
Yeah.
this for just for 3 manifold?
No, that's amongst everything.
Yeah.
So that's amongst all finitely generated residually finite groups. That's a reasonable thing to ask about, to what extent Coxeter groups could be determined by the finite quotients or right-angled Artin groups.
Yes.
I would probably bet yes. Yeah.
30, 40 years ago in quantity theory and topology, the sort of question to consider sort of a genus and profinite completions. It was a sort of beautiful theorem, I don't remember exactly which one, proved the sort of analogous of your rigidity, but in that context, where 2 spaces actually seem to connect to a finite count. So you have the same profinite completion in commutative theoretic sense. They are commutative or not. Are you aware of this type of things?
No, I don't think so. You can tell me more about that later.
Yeah, we are. Well, I have to.
You can.
I'm not just sympathy, but if you dig out a little bit, this sort of thing to find out this question.
Right.
Also,
This is like Guido worked on this. Or something.
I suppose so.
But you're not talking about the fundamental group. right?
No.
Well, yeah, but that's sort of more sophisticated thing where simple spaces are not simply connected. Guido is the expert for the question of localization and profinite completion for simple connected things. There is also the question which is very related. Well, this picture of a simple connected case analogous to what you said at the very beginning is an important test. Yes, I mean, a theorem like that, analogous theorem like that in this context, it probably is the same type of proof.
So taking the pro-nil completion or something?
No. I don't mean to say 2 spaces, integrated spaces, but with localization at any prime P are commutatively equivalent of all this sort of thing. How many such spaces exist? And for example, there are hardly many, at least in the large class of spaces, this type of theorem we mentioned before, of a pseudo
Yeah.
is analogous sort
I
of
see.
thing like that. Yeah, well established, I even remember. All these things.
That's interesting.
But there is another sort of thing, analogous of the question of lattices we have mentioned. But there is also in homotopy theory, there is sort of spaces which, let's say, fundamental group is like a lattice or let's say not nice group, which acts semi-simple on the other high homotopy groups. For those things we define localization, profinite completion, anything like that. And there was theorem like that, but I cannot tell you anything too much. In any case, just looking about this sort of thing is nice to dig a little bit in literature to see what these people have done.
I see. I should look at that.
And there were very beautiful sayings, I mean, about.
Okay, maybe more questions? Okay, thank you, speaker.